Okay, so in the last two videos, I have talked about radon measure. Now I thought that it's a very nice idea to go through this concept called Haar measure. I mean, this is very important in number theory, representation theory. I mean, whatever you study, probably in every branch of mathematics, you will find some application of Haar measure. It's a very ubiquitous thing. Uh, so let me explain what is a Haar measure. So suppose you have this locally compact Hausdorff group. So okay, so first of all, let me explain what is a topological group. So suppose you have a topological group G. So what is the meaning of that? So G is a set on which you have a group structure, on which you also have a topology, and these two operations are compatible with each other. So that means what? That means if you look at the group operation from G cross G to G, the G comma H goes to G H inverse. This group operation is continuous in the given topology of G. So you can guess the definition more or less from the terminology, topological group. That means you have a topology on a set, you have a group structure on a set, and these two structure has to be compatible if this term has to make sense. So that is topological group. Now, if the topology is locally compact Hausdorff, we call it a locally compact Hausdorff group. In short, LCH. I will use this shorthand notation LCH for locally compact Hausdorff group. And so, what is the interesting thing about this topological groups? So, this topological groups has a very uniform structure. So, if you look at the left multiplication map, if you look at the map which takes x to gx, that means I'm looking at left multiplication by g. You can check that this is a homeomorphism. This left multiplication by g is a homeomorphism. That means if you take a neighborhood of the identity, let's say u, so that will get mapped to gu homeomorphically, and you can go back to u by applying g inverse. So this is the thing. You can go from here to here, you can come back from there to there. So the topology has a very uniform structure in a topological group. Now, so one sensible guess. So, so I want to cook up a radon measure on a locally compact group because I know that locally compact groups are very nice because we already discussed in the last two videos that in a locally compact Hausdorff space, um, we have this Ries representation theorem. That means your linear functional, positive linear functionals on compactly supported continuous functions corresponds to some unique radon measure. So locally compact spaces are very nice. So one sensible guess is that in a locally compact Hausdorff group, probably we can cook up a measure which is not only a radon measure, but it is also invariant under the action of the group. And fortunately, this is actually true for locally compact Hausdorff group. So, so the volume of the set U is same as volume of the set GU. GU means the left translate of U by G. So that means not only your topology has a uniform structure, your measure also has a very uniform structure. The volume are distributed uniformly throughout G. I mean, what can be better than this? And this is a very beautiful thing. I mean, the best thing you can expect is actually true in case of locally compact Hausdorff groups. So yeah, so you have a topology on some space, you have a measure on some space, you have a group operation on some space, and all these three things are compatible with each other. So this kind of left invariant measure. So in a locally compact Hausdorff group, you can cook up a radon measure which is left invariant. So that means this condition holds that measure of U is same as measure of GU. This is left invariant radon measure. Simply, similarly, you can define right invariant radon measure, which of the property that measure of U is same as measure of UG. That means you have to take G on the right. So any locally compact, this is a very important theorem that any locally compact Hausdorff group has a left invariant Haar measure. Similarly, there is a right invariant Haar measure. Now the thing is that left invariant Haar measure may not be equal to right invariant Haar measures. And if in a group these two things coincide, that left invariant Haar measure is also right invariant and vice versa, those kind of groups are called unimodular groups. I mean, those are very important in number theory. And also those are connected to study of the upper half plane. Sometimes people study this upper half plane in number theory where they put something called hyperbolic measure. So there the study of unimodular groups actually helps. So yeah. So that is the thing. So the upshot that I'm trying to say is that in any locally compact Hausdorff space, you have a measure so that all these three things are compatible with each other. This topology, because you already know that in a radon measure, topology and measure are already compatible. And I'm putting an extra thing, the group operation. And surprisingly, in locally compact Hausdorff group operation is also compatible with the topology and the measure. So this kind of measure is known as Haar measure, which is countably additive. And this Haar measure has two properties. This is countably additive, and also this is unique up to a scalar multiple. That means you can scale the volume of each subset by some fixed constant. Let's say you can double the volume of each subset, or you can half the volume of each subset. But there is to be a fixed constant. So this is unique up to a scalar multiple. So now let us study what happens if G is actually compact. Because in mathematics, I mean, compact spaces are always nicer than locally compact. Even if you want to study representation of compact groups, that is nicer than locally compact ones. Locally compact things can be way more difficult than compact ones. So let me now only focus on compact things. So what happens if G is compact? So what I have already said is that in a locally compact Hausdorff group, uh, there is a radon measure which is left invariant under the action of G. So we know that radon measure is already finite on compact sets. So since my G is compact, so measure of G is finite. And the Haar measure is unique up to a scalar multiple. So I can normalize the Haar measure in a way so that measure of G becomes 1. It's a very nice thing. That means mu becomes a probability measure. These are the best thing you can expect. That on a compact space, you can put a probability measure, which is left invariant and also right invariant. By the way, for compact groups, left invariant measure and right invariant measures, Haar measures, left invariant and right invariant Haar measures coincide with each other. Compact groups are always unimodular. Compact groups are very nice. So, I mean, even in ergodic theory, this has some very deep implications. So, whatever you do, number theory, ergodic theory, representation theory, these things are very basic tools which you need to know. Uh, yeah. So that's what I was saying, that you can normalize the measure in a way so that it becomes a probability measure. So on a compact group, you have a probability measure. Uh, yeah, that's what I have written here. That I said already, that for compact groups, left invariant Haar measure coincide with right invariant ones. That is, compact groups are unimodular. And now I want to talk about representation theory, which is my area of interest. how does Haar measure help us in representation of theory of compact groups? So first let me recall what is the definition of a representation. So representation means a group is acting on a vector space in a linear way. Now of course, if some group is acting on a vector space, this action better be compatible with the structure of the space. So on a vector space, I have a linear structure. So I want this action to be compatible with the linear structure that is already given on my vector space. So that means a group is acting on a vector space which satisfies this additional condition that g dot lambda v1 plus v2 is equal to lambda g dot v1 plus g dot v2, where lambda is a scalar and v1 and v2 are arbitrary vectors in V. So that means my G is acting linearly on a vector space V. So that is the definition of a representation of a group G on a vector space V. Okay. So now what happens? So there is an important thing called completely reducible representation. So what are completely reducible representations? So if V can be written as, so V can be, if your V can be written as, if your V can be written as is direct sums of subspaces, each of which is G invariant. That is, V can be written as direct sum of VI's where each VI is G invariant. And also I should write this thing, each VI is also irreducible. That means you cannot break VI further. You cannot break VI into direct sum of two subspaces further so that each of them is G invariant. Yeah, I hope you can understand what I'm trying to say. So this VI cannot be broken further into two subspaces so that W1, W2, both of them are G invariant. So that means these VIs are irreducible copies. So if V can be written as direct sum of these irreducible copies, each of them is G invariant. By G invariant, I mean G dot Vi is contained in Vi for all G in G. So this Vi is a G invariant. So if this V can be written as these G invariant irreducible subspaces, then this kind of representation is called completely reducible. Okay. Okay, so right now let me only focus on finite dimensional ones, finite dimensional representation. Uh, by the way, for compact groups, the study of infinite dimensional representation actually reduces down to finite dimensional ones. This is also a very deep theorem. Compact groups are very nicer. There is a famous theorem that irreducible representations of compact groups are always finite dimensional. So even if you want to study some infinite dimensional representation, ultimately it boils down to studying finite dimensional representation. So let me only focus on finite dimensional representation. Now for compact group, what happens? So in general, when you study a representation of a group, then a representation may not be completely reducible. So for finite groups, we have this powerful theorem called Maschke's theorem, which helps you to prove that a representation of a finite group is completely reducible. And Haar measure actually helps us to prove the same theorem for compact groups. Using Haar measure, so how to prove this? Any representation of a compact group is completely reducible. So how to prove this? So idea of the proof. So introduce a G invariant, and these are powerful thing. Okay, I mean this idea is applicable in many places in representation theory, as far as my experience goes. Uh, that on a vector space, see, vector spaces are just abstract spaces which are some linear structure. But if you want to study vector spaces better, you can introduce a geometric structure. And concretely, what a geometric structure means? Geometric structure means you have this notion of length, distance, angle. These things are concrete geometric concepts. And how can you introduce such concepts? You basically introduce the inner product, right? Inner product gives you the notion of length, distance, angles, and so on. Yeah, so idea of the proof is that introduce a geometric structure that is an inner product and which is also G invariant. So that means precisely if you want to write, then you can write in the following way. The G invariant means the inner product of two vectors is same as G dot V comma G dot W. Inner product of V and W is same as G dot V, inner product of G dot V and G dot W. That means the measurement is unchanged after the operation of G. Okay. So how do you now? So how do you introduce a inner product which is invariant under the action of G? That is this satisfy this condition. So the idea is basically is that choose an arbitrary inner product. You can always choose an arbitrary inner product on arbitrary inner product on um, V in your vector space. They choose an arbitrary inner product and then you can average. That is the main idea. So you can define a new inner product. So let me call it averaged. This is an average inner product. How do you average? You integrate over the group. Okay. So this is already a function of G, the inner product of G dot V and G dot W, and then you integrate against the Haar measure. So this is your Haar measure that we have already constructed. I mean, we have not proved it. I have just stated the result, but you can look the proof in many places. This is a very standard one. Um, yeah, so we can define this new inner product. So basically, I'm integrating this function that g dot v comma g dot w over the group. That means I'm basically averaging the inner product over the group. This is a very common trick in mathematics. When the group is acting on some space and you want to make some property of the space invariant under the group, you take an arbitrary property and then you average over the group. This is a very common philosophy, very natural thing. So integrate this function against the Haar measure, and since the Haar measure is group invariant, I mean left invariant under the action of the group, this new inner product will also be invariant under G. That is a beautiful thing. So this will be equal to G dot V comma G dot W average, because average means I am talking about this new inner product, not the old one. The old inner product may not be invariant, but after the average it will become invariant. So yeah. So whenever you have this inner product which is invariant under the action of the group, then your representation will be completely reduced. Okay. Okay. So now let me create a new page. Yeah. So you have this V, and suppose there is a subspace of V so that this W is G invariant. Okay. So since you have an inner product which is G invariant, so this V will break up as W directs some W perpendicular. That is the main trick. You have a inner product which is G invariant and which is also, I mean, it's a non-degenerate. It's a non-degenerate bilinear form. So that's why if you take the perpendicular of W with respect to that inner product, I hope you know what is the meaning of W perpendicular. W perpendicular means what? I have to look at all x in V such that inner product of x comma W is 0 for all W in W. That means I'm looking at the perpendicular space of W. So since you have this G invariant geometric structure, this V will be split into the direction of W and W perpendicular. First of all, if W is G invariant, that is G dot W is contained in W, you can also check that W perpendicular is also G invariant. That is very easy to check. Because see, uh, because if X belongs to W perpendicular, that implies what? That implies that X W inner product is 0 and my inner product is invariant under the action of the group, right? So I can push a G inside, that will also be 0. And since W is G invariant, that means GW is contained in W. So G dot X comma W prime is also 0, but W prime is some element of W. So that means this this Gx belongs to Gx also belongs to W perpendicular. So if X is in W perpendicular, Gx is also W perpendicular. Because of this G invariance of the inner product, this thing follows. So this W is also invariant, this W prime is also invariant. So I have broken V into pieces, two pieces, each of them are G invariant. And then you can proceed by induction. You can again break W. You can see if this W has some subspace which is G invariant, and then again break W. Then you can check if W perpendicular has some invariant subspace, and by induction on the dimension of V, this V will break up into irreducible subspaces. Irreducible means it cannot be broken further. Some finite even is subspace. So exactly what is the role of the Haar measure? So let me summarize the whole thing using kind of flow chart. You can say that you have a compact group G, then that gives you a Haar measure, that gives you a G invariant inner product on V. V means the space that is G is acting on, and from that V breaks up into direct sum of irreducible subspaces. So that means any representation is completely reducible. So we can recover complete reducibility in case of compact groups also. Mask's theorem deals with finite groups, but using Haar measure, that thing can also be recovered for compact groups also. So let me summarize what I have discussed in this video. So my main goal was to show that how an important measure, namely the Haar measure, can help us do some remarkable thing in representation theory. That is introducing a G invariant inner product. Okay, so yeah, so first of all, the main theorem is that uh, yeah. So let me go back to that slide. Yeah, yeah. So you have a topological group, and then this topological group has a very uniform structure. And in locally compact Hausdorff topological groups, there is a radon measure which is also left invariant, and also there is a radon measure which is right invariant. So locally compact spaces are very nice in that sense. So you see that this locally compact Hausdorff spaces are very nice. So in the last video I talked about Rees representation theorem, and now you have this Haar measure. These are remarkable things, which is not true for arbitrary spaces. The locally compact Hausdorff spaces are pretty good, and that's why these are interesting object to study. Uh, and in locally compact Hausdorff group, one can cook up a measure which is invariant under the action of the group, which is known as the Haar measure. Uh, this Haar measure is countably additive, tuning up to a scalar multiple, and when G is compact, then you can normalize the measure so that the whole measure becomes one, which is a probability measure. So on every compact group, I have a probability Haar measure, and then you can Haar measure. Using Haar measure, you can use that to prove the complete reducibility of any representation for compact. So really, that's all I wanted to say. So probably in future, I may come up with more videos. I mean, which are related to this locally compact Hausdorff spaces. Uh, Maybe some more interesting applications in number theory and representation theory also. I do not know too much about ergodic theory, but you can look up yourself. So, okay, so goodbye. And if you have any questions or doubts, so feel free to ask in the comment section.